Welcome back to the deep dive. Today, I actually want to start by asking you to do something really simple. Just, take a second and look around the room you're currently sitting in.
Okay. Look
You
good.
probably see a chair, maybe a window, a coffee mug on your desk. And it feels entirely instantaneous.
Right.
You don't actually have to think about the act of seeing.
Right, yeah. That's the whole illusion of human perception. I mean, it feels effortless to us, but biologically speaking, it's an incredibly complex data processing task.
Exactly.
Hmm.
And for decades in the world of artificial intelligence, uh, seeing was actually one of the absolute hardest problems to solve.
It really was.
But I mean, we've had computer vision for a while now, though. Like,
Yeah.
my phone gallery knows what a cat looks like. It groups all my cat photos together.
Right, but it knows what a picture of a cat looks like. And that
Yes.
is a really crucial distinction for what we're talking about today. Traditional AI, it sees pixels.
Right.
It classifies patterns in those pixels, but it doesn't really perceive the way you and I do. It doesn't look at a messy handwritten note and understand the intent behind the scrawled ink, or watch a 20-minute video and actually get the plot of what's happening.
It just sees a sequence of static, disconnected images.
Exactly.
Well, today, we are digging into a stack of research that claims we are finally crossing that exact threshold. So our mission today is to unpack a new model series from the Qwen team at Alibaba Group. It's called Qwen2-VL.
And the VL stands for vision language.
Right, and we're basing this deep dive on their technical report, which is titled Qwen2-VL, Enhancing Vision Language Models' Perception of the World at Any Resolution. Plus, we've got a whole stack of qualitative examples and benchmark results they provided.
It's a lot of material.
It is. But the core promise here isn't just, slightly better image recognition. We're looking at how this model redefines visual processing by actually mimicking human perception, giving machines native eyesight.
And what makes this so fascinating is that they aren't just doing the brute force thing. They aren't just throwing more computing power at the problem and hoping it gets smarter.
Right.
They actually went back to the drawing board and fixed fundamental flaws in how AI models look at the world. Specifically, they tackled the resolution problem, the time problem with videos, and the agency problem.
Yeah, so let's start with that first one, the resolution problem. Because reading this in the technical report was the first thing that actually made me laugh out loud.
I know exactly what you're going to say.
I just had no idea that most of the cutting-edge AI models we rely on today basically have terrible eyesight.
It's incredibly ironic. We call this the fixed resolution constraint.
Can you break that down for us? How does that actually work?
Sure. So imagine you have a beautiful high-definition panoramic photo of a city skyline, or
Right.
maybe a really tall, thin infographic you found online.
Okay.
When you feed that image into a standard large vision language model, an LVLM, the model doesn't actually see the image in its original shape.
Changes the shape.
It forces it into a square.
Just automatically.
Yeah, usually a 224 by 224 pixel box.
224 by 224.
Mhm.
That is, that's tiny. That's like an internet thumbnail from 1998.
It really is. So think about what happens to your image. If it's a wide panorama, the AI literally squashes it horizontally to make it fit that square box.
Oh, wow.
If it's a tall skyscraper, it squashes it vertically.
Which ruins the detail.
Completely. Or if the developers don't want to distort the image, they'll shrink it down proportionally until it fits inside the box, and then they just fill the rest of the empty space with black pixels.
Which just sounds like wasted data.
It's massively wasted computation. It's a one-size-fits-all approach that essentially blinds the model to any fine details.
Why on earth would engineers ever design it that way to begin with? It sounds incredibly inefficient.
Well, it was an engineering shortcut, basically. If every single image is the exact same size, just a neat little square, you can stack them all together in batches.
Oh, for the hardware.
Exactly. You push them through the graphics cards, the GPUs, much, much faster. It made the math highly predictable.
So they essentially sacrificed actual vision for processing speed.
They sacrifice detail for manufacturing ease. But Qwen2-VL completely tosses that old method out the window. They use a totally different approach called naive dynamic resolution.
Okay, naive, which usually means dumb in tech parlance, but here I think it means pure, right, or native.
Native is the perfect word for it. It takes the image exactly as it is. If you feed the model a skyscraper, it processes a tall, thin strip of data.
Nice.
If you feed it a wide panorama, it processes a wide strip. It converts the image into what we call visual tokens. You can think of these as little packets of visual information, and it dynamically generates these tokens based on the actual resolution and clarity of the original file.
So it's not squinting or squashing things anymore.
No, not at all. It uses a massive vision transformer, which has about 675 million parameters to digest all these tokens.
But wait, if you're feeding a raw, high-resolution image into a brain that big, wouldn't the computing cost be astronomical? Like, it would be way too slow for anyone to actually use.
And that is usually the trade-off, yeah. Better vision usually equals a much slower brain.
Right.
But the Qwen team implemented a really clever pooling layer. Specifically, it's a 2x2 convolution.
Okay, what does that mean in plain English?
Imagine taking a grid of 4 adjacent pixels on an image, 2x2.
Got it.
The model compresses those 4 pixels, summarizing them into one single rich data token before sending it up to the brain of the model.
Oh, so it shrinks the data footprint.
Exactly. It compresses the visual representation by a factor of 4, so you still get that high-definition clarity from the native shape, but the token count, the file size, basically, stays totally manageable.
That's brilliant.
It is. A standard 224 by 224 image becomes just 66 tokens.
Wow.
But a massive, complicated chart with tiny text, that gets as many tokens as it needs to be readable.
Which aligns perfectly with human perception.
Right. You don't burn the same amount of mental calories staring at a blank white wall as you do reading a dense textbook.
That makes total sense. It feels like the difference between staring at a blurry thumbnail and actually being able to zoom in on the details. And I'm assuming this is why the model can handle things that usually break other AIs, like complex documents.
It's the absolute foundation for everything else it does. If the model can't see the fine print, it can't read the contract.
Makes sense.
But seeing static 2D images clearly is really just step one, because the real world isn't a static photograph.
Right. It's moving. It's 3D.
Exactly. And this brings us to the acronym of the day from the technical report, MROE.
MROE, Multimodal Rotary Position Embedding, which sounds like a very complicated piece of climbing gear, but I know it's math.
It's heavy math.
Yeah.
But we can simplify the concept. Think about standard language models, the ones that just process text.
Like standard chatbots.
Yeah. They view the world as a straight one-dimensional line. Word 1, followed by word 2, followed by word 3.
Like an old school ticker tape.
Precisely. It's 1D. But a video isn't a ticker tape. A video has height, it has width, and it has time.
It's a 3D volume of data.
Right. But previous models tried to basically unroll that video into a long, flat line so their text-based brains could process it.
And I'm guessing that's where the context completely gets lost.
You lose the spatial and temporal relationships. If you flatten a video, the model might forget that the coffee cup in frame 1 is in the exact same physical location as the coffee cup in frame 2. It loses the concept of where things are.
So how does MROP fix the ticker tape problem?
It decomposes the position information. Instead of just giving every single piece of data one sequential number like 1, 2, 3, it gives every token 3 distinct IDs.
Okay.
A temporal ID for time, a height ID, and a width ID.
So it's essentially a 3D GPS coordinate system for the data.
That's a great way to think about it. For plain text, it just uses the 1D part. For static images, the time variable is frozen, but the height and width IDs vary based on where the pixel is.
And for video?
For video, think of it as a solid 3D block. The model knows that a specific visual token is located at coordinate X, coordinate Y, and time 4.
Meaning it can track movement perfectly. Because it knows that at time 5, that exact same pixel or object has moved to a new X and Y coordinate.
Correct. It allows the model to connect the dots across time and space simultaneously. It actually understands that the blue blur in the corner of the frame is the same person walking across the room over a 10-second span.
That's fascinating. And the report mentioned this MROP architecture allows it to handle videos up to 20 minutes long, which seems huge.
It is.
Most of the multimodal models I've played around with just completely choke after about 60 seconds of video.
20 minutes is a lifetime in AI processing. And the reason it can do that goes back to the variable resolution we talked about. Qwen2-VL treats images and videos as part of the exact same pipeline.
How so?
It just treats a static image as 2 identical video frames. And for actual videos, it samples them at a rate of 2 frames per second.
Okay, so it's not processing 60 frames a second, which would be overload.
Right, so a 20-minute video isn't just a massive blur of data. It's a neat sequence of thousands of highly detailed, high-fidelity observations.
There was a great example of this unified understanding in the source material, the one with the astronauts.
Oh, yeah, where the model watches a video of people floating in a space station.
Right. If you ask a standard model what's happening, it might just give you a generic tag like people in space. Boring. But Qwen2-VL watches it and accurately describes their clothing. It notes the blue and black suits. It tracks their movement through the station.
But my absolute favorite example from the qualitative data was the cleaning video.
The vacuuming one.
Yes. The model is shown a video of someone vacuuming a floor, and the prompt just asks, what happens next?
And what does it say?
The model suggests mopping.
That is wild, because that implies it actually understands the process, not just the visual shapes on screen.
Exactly.
It knows that cleaning is a logical sequence of events. Vacuum first,
Yeah.
mop second.
And that is the fundamental difference between just seeing and truly perceiving. It's reasoning about how the physical world works based purely on visual input.
Well, speaking of reasoning, we should definitely talk about the scholar capabilities. Because we've established it has 20/20 vision and it understands the flow of time. But can it read? And I don't mean parsing a clean digital PDF. I mean the absolute nightmare scenarios.
Nightmare scenarios being what exactly?
My handwriting, for starters.
Yeah.
Or trying to read a blurry menu in a dark restaurant in a foreign country.
Well, you are in luck, because the model's multilingual OCR, its optical character recognition, is an absolute beast. The research team tested it on this incredibly dense image that contained 16 different languages.
16?
Yeah, Greek, Russian, Thai, Arabic, mostly European languages, Japanese, Korean, Vietnamese, all jumbled together on one image.
How did it do?
It didn't just transcribe them perfectly, it successfully identified which language was which.
That's impressive.
But for your handwriting problem, there's a very specific case study in the report you'll love. They gave it a handwritten letter in Chinese that starts with, respected teacher.
Handwriting is notoriously brutal for AI because everyone's personal font is entirely different.
It's very tough. But the model transcribed the Chinese characters perfectly. But here's the tiny detail that really caught my attention. It didn't add any punctuation.
Wait, why is that a good thing? Wouldn't you want the AI to fix the grammar as it transcribes?
Not if you want true transcription accuracy. The original messy handwritten note didn't have punctuation in it. Most AI models will hallucinate in that scenario.
Oh, they guess what should be there.
Right, they'll just sprinkle in commas or periods to make the output look structurally nice. But Qwen2-VL was disciplined enough to transcribe exactly what it saw, nothing more. That implies a level of strict control that is very rare in LLMs.
It also tackled some serious academic literature. I saw a benchmark where it analyzed a page from a Chinese textbook.
Right, it was a page comparing poems by Guamaru and Percy Bysshe Shelley.
The Goddess and To a Skylark.
Exactly. And this wasn't just recognizing the printed words, it was reading for meaning. It actually translated the literary analysis of the page into English and captured the emotional context. It even picked up on the historical reference to the May 4th movement.
So it requires underlying cultural knowledge, not just good OCRIs.
Precisely. And it does this for general knowledge, too. It can identify specific flowers, like forget-me-nots from a photo, or look at a raw screenshot of Linux kernel versions and automatically list out all the release dates formatted as a JSON file.
Amazing. But then there's the math. I'm looking at this one example they provided of a page full of limited linear series equations, and honestly, just looking at the image gives me a headache. It's so dense.
And this brings us right back to the revolution we started with. Mathematical formulas entirely rely on tiny, tiny details. Subscripts, superscripts.
Right.
If you squash that math textbook page into a 224 by 224 square, a superscript X just looks like a meaningless speck of dust. The AI literally can't see it.
But because Qwen uses the native dynamic resolution,
It sees the X. It sees the tiny minus sign. In the example, it converted that entire dense page of formulas into clean markdown code. It effectively translated a complex image into a fully programmable format.
and it doesn't just format it, it solves the math too. The isosceles triangle problem in the report really drove this home for me.
Right. So the model is shown a diagram of a triangle. The sides are labeled with algebraic expressions like 9x minus 1 and so on. The model has to successfully do three entirely different things here.
Okay.
One, it has to accurately read the messy algebraic labels from the image. Two, it has to understand the geometric rule that an isosceles triangle means two sides are equal.
Right.
And three, it has to logically set up the equation based on that rule and mathematically solve for x.
And it got the answer. Right. It was 7.
It got 7, and it showed all its work step by step.
It also did 3D geometry, right?
Yeah.
calculating surface area and volume of a rectangular prism and a cube, just from looking at a diagram.
Yes, and it extends to algorithmic reasoning, too. There was a great example where it looks at a screenshot of a snake-in-matrix coding problem,
Oh, I saw that.
and it just writes the correct Python code to solve it. It defines the movement functions, like move right and move up, based entirely on the visual prompt.
Okay, so it's a mathematician, it's a linguist, it's a programmer, and a film critic. But here is where I really want to pivot, because this next part is what I think is the most genuinely disruptive part of this entire report, the shift from passive observer to active agent.
This is the real so what of the entire deep dive. The researchers refer to it as the VL agent, vision language agent.
Because up until now, if I want an AI to, say, book me a flight, there's a lot of unseen plumbing involved.
Yeah.
The AI needs to connect to an API, a back-end system that directly talks to the airline servers. It's code talking to code.
Exactly. And if the airline doesn't happen to have a clean API, the AI is completely helpless. It can't do anything.
But Qwen2-VL completely flips that dynamic. There's an example where the user just shows the model a screenshot of a flight ticket, Air China CA1723.
Right. The model looks at the image and extracts the arrival time. But then it does something very human.
Yeah.
It decides it needs to check the weather for the user. So it autonomously calls a weather function for Beijing, specifically targeting that exact arrival time it read off the ticket.
It's connecting the dots on its own. I see a flight, I see a time. The user's going to need to know if they should pack an umbrella.
And it reports back, it will be raining with a temperature of 27 degrees Celsius. That's incredibly useful function calling. But honestly, the mobile phone navigation example is the real game changer here.
This one blew my mind. The user prompt is just, find a pizza restaurant.
Think about what the AI actually has to do to accomplish that. It is looking at a live visual stream of a mobile phone screen. It sees the physical home icon on the UI. It doesn't have a backdoor line of code that says click home. It has to physically, well, virtually, locate the exact pixels of that home icon and generate a precise click command at those spatial coordinates.
Then it scans the app drawer visually, finds the map's icon, clicks that, then goes to the search bar and types in pizza.
Step by step. It's operating the software the exact same way a human being does, by looking at the graphical interface.
So let's pause on that for a second. If an AI can operate any app just by looking at the screen, doesn't that fundamentally mean every single piece of software ever written is now API compatible with AI?
That is the exact implication, yes. You don't need to build special AI integrations or plugins for your legacy software anymore. If a program has a screen that a human can use, the AI can drive it. It bypasses the need for a backend entirely.
That is massive. It turns the entire visual web into a playground for these agents.
And the benchmark tests back this up. They tested the model on agent benchmarks like AppAgent and R2R, which stands for Vision Language Navigation.
And how did it score?
It achieved state-of-the-art results. It's not just clicking randomly and getting lucky. It shows really high success rates in type match and exact match for complex function calling.
Okay, we've been hyping up the capabilities a lot, but let's talk about the models themselves. Because we need to know, is this one giant, unapproachable supercomputer brain? Or are there versions I can actually run on my own hardware?
They released a full lineup to investigate what we call scaling laws, basically checking to see if a bigger model is always inherently better. So there are 3 distinct sizes. Qwen2-VL2B is the baby of the group. 2 billion parameters.
Which is small enough to run natively on a mobile phone, right?
Potentially, yes. It's highly efficient, designed specifically for edge devices. Then you have the 7B, the 7 billion parameter model.
Okay.
That's your cost-effective workhorse. It's optimized for processing long videos and doing heavy text recognition without breaking the bank on compute.
And then there's the Godzilla model.
The Qwen2-VL72B. This is the flagship. When we talk about the really complex reasoning, the deep math problems, the nuanced 3D video understanding, this 72 billion parameter model is the one doing the heavy lifting.
So the big question is always the same with these new models. How does the flagship actually compare to the heavy hitters we already know, like GPT-4o from OpenAI or Claude 3.5 Sonnet from Anthropic?
The Qwen team definitely brought the receipts on this. Let's look at the Doc VQA benchmark, Document Visual Question Answering.
Right.
This benchmark is essentially looking at terrible scanned receipts with coffee stains on them and answering questions like, what was the local tax rate applied?
A literal torture test for bureaucracy.
Exactly. The 72B model scores a 96.5 on this.
And the competition.
GPT-4o scored a 92.8. Claude 3.5 Sonnet was closer at 95.2, but Qwen is clearly winning here. It is practically superhuman at paperwork.
That is seriously impressive. What about Math Vista? That's the visual math reasoning benchmark.
On Math Vista, Qwen2-VL scores a 70.5. GPT-4o was sitting at 63.8. That is a very significant performance gap. It strongly suggests that this native dynamic resolution approach really pays massive dividends when high precision is required.
But is it winning across the board everywhere? What's the catch?
No, it's not winning everywhere, and we should definitely be balanced here. On the MMMU benchmark, which tests extremely complex, multidiscipline reasoning, think college-level cross-domain problems,
Okay.
on that one, it still lags slightly behind GPT-4o. So it suggests there's some room for growth in extremely complex multi-step problem solving. It's not the absolute smartest at everything, but for visual perception, document handling, and video, it is right at the bleeding edge.
And perhaps the most significant part of this whole release for the developers and researchers listening who actually build this stuff.
The ways are open.
Right. Because GPT-4o is a walled garden. It's a black box. We send our data in through an API, we get answers out, but we don't own or see the brain.
But with Qwen2-VL, the 2B, 7B, and the massive 72B models are open weight. You can download them, you can fine-tune them entirely on your own proprietary data.
Which is huge.
For researchers and enterprise companies who care deeply about data privacy or custom domain-specific tuning, this is a massive democratizing force. You get GPT-4 level vision, but you control the model.
So to try and wrap this all up, we are looking at a model that fundamentally sees the world in its native resolution. It understands the 3D flow of time in long videos thanks to MROPE. It can read the messiest handwriting imaginable without hallucinating. And it can operate our phones and apps just by looking at the screen.
It really feels like we are watching the physical barrier between the screen and the data dissolve in real time.
It makes you wonder about the long-term future of the interface itself. I mean, we spend so much time and money designing buttons and drop-down menus specifically so that human beings can understand how to talk to the computer.
Right.
But if the computer can now see and understand the visual interface just as well or better than we can,
then maybe we stop designing graphical interfaces for humans altogether, or maybe the interface just disappears entirely.
Right. If the AI agent can navigate the complex menus instantly, why do I personally need to see the menus? Maybe we are actually the last generation of people that will spend our days tapping on glass screens.
That is a very real possibility. The universal interface of the future might just be vision.
A fascinating, if slightly eerie, place to leave it. Thank you so much for walking us through the Qwen2-VL series today.
Always a pleasure to be here.
And to you listening. The next time you're forced to solve a picture captcha with traffic lights to prove you're not a robot, just remember, the robots are getting really, really good at it. Thanks for tuning in to The Deep Dive. We'll see you next time.